Hi everyone, it's my great honor to present our work, Primate Approximation of Convex Hull in Low Dimensions. It's a joint work by me and Sheffet. We respectively affiliate to University of Alberta and Bar-Ilan University. We want to approximate the geometric features such as minimum bounding ball radius, diameter, convex hull, and width in low-dimensional Euclidean space. Usually, the dimension is 2 or 3 or 4. What do people do now is to compute those geometric features directly. They just reveal those features as it is, without any privacy protection. But here's an example. On the right-hand side of the figure, where the dataset is got by just adding one more data point compared to the left figure. It changes these geometric measurements drastically. Where here, the diameter is defined to be the maximum distance between two data points, and the width is defined to be the minimum distance between two parallel hyperplanes sandwiching the dataset. So our motivation is to find a geometric notion which is more robust in the sense that it does not change drastically with the addition or removal of a single datum. And we also want to approximate those geometric notions privately. Differential privacy is a commonly used tool to preserve privacy in the sense that the output of algorithm does not reveal any individual's information. In DP algorithms, we often need to use functions as queries. The key technique in differential privacy is to release query plus a noise term. And this is workable when the sensitivity of query is small, and not workable when sensitivity of query is large. Laplacian mechanism is a widely used simple differential private algorithm, where for the query of sensitivity delta, the output of the algorithm is to add a Laplacian noise with a scale parameter delta over epsilon. And note from this utility guarantee that the robust measurements are easy to preserve. However, the measurements that can vary significantly by a single datum are hard to make into private. For a given dataset P, for a point x in the space, the Tukey depth of x is defined to be the minimum size of a subset S of P such that there exists a hyperplane separating x from P minus S. As shown in the left figure, the black solid circles denote data points. For the purple crossing point in the space, although hyperplane H2 separates 3 points from the dataset, the hyperplane H1 separates the smallest amount of points from dataset, and it only separates 2 points. So, the Tukey depth of the purple crossing point is 2. Note that since by adding a single data point, for any hyperplane, the number of points separated from the dataset differ by at most 1. So, the sensitivity of Tukey depth is at most 1. The figure on the right is an example. The dataset is got by the dataset on the left plus a single red datum. And the Tukey depth of the purple crossing point is still 2. Since the hyperplane H3 separates two data points from the dataset. And note that for a d-dimensional dataset of size n, the Tukey depth is upper bounded by n over 2, and there must exist a point in the space with Tukey depth greater than or equal to n over d plus 1. Kappa Tukey region is defined to be the set containing all points with Tukey depth greater than or equal to kappa, and the time complexity of computing a non-empty Tukey region is big O of n to the power of d times log n. So, the time complexity of computing all of the non-empty Tukey regions is big O of n to the power of d plus 1 times log n. As shown in the figure, d1 is denoted as all of the points in the space whose Tukey depth is greater than or equal to 1, which is an alternative name for the convex hull of the data points. And the 2 Tukey region d2 is denoted as all of the points in the space whose Tukey depth is greater than or equal to 2. You can note from those figures that, although for neighboring datasets the sensitivity of Tukey depth is at most 1, Tukey regions can differ a lot by replacing or adding or deleting a single datum. And note that the deeper the depths are, the smaller the Tukey region is. One of our goals is to privately approximate geometric features, including width and diameter. We give the bicarriterial notion of those features. For Kappa Tukey region, those bicarriterial measures lying between the 1 minus alpha scaling of the measure of Kappa Tukey region and the 1 plus alpha scaling of the shallower Kappa minus delta Tukey region. We propose differential private algorithms to approximate those bicarriterial measures of Tukey regions. Note from those notions that the accuracy of the measure approximation is always related to how close the Kappa Tukey region and the Kappa minus delta Tukey region are. For example, on the left figure, the Kappa Tukey region and Kappa minus delta Tukey region are similar. So from the notion, if L is an alpha-delta approximation of the diameter of Kappa Tukey region, then L is quite close to the true diameter of Kappa Tukey region. However, for the right figure, where the Kappa minus delta Tukey region is much larger than the Kappa Tukey region, then if L is an alpha-delta approximation of the diameter of Kappa Tukey region, it may differ a lot from the true diameter of Kappa Tukey region. Here's an example of a bicarriterial approximation of convex hull of Kappa Tukey region. On the left side, Kappa Tukey region and Kappa minus delta Tukey region are quite similar. So the bicarriterial approximation B is a good approximation of convex hull of Kappa Tukey region. While for the figure on the right, Kappa Tukey region is quite small compared to the shallower Tukey region. So although B satisfies this bicarriterial definition, we can see that this approximation is not that accurate. Note that in our paper, we also do this bicarriterial approximation for kernel. So, what does kernel mean? In their seminal paper from 2004, Agarwal et al. Motivated from the perspective of a more efficient algorithm for approximating the convex hull, defined a kernel to be a subset S of P, where for any direction U, it holds that the directional projection of S is upper bounded by the directional projection of P and is lower bounded by 1 minus alpha scaling of the directional projection of P. In private case, we cannot directly release data points since that will violate privacy. So, in private case, we don't use the condition that S be a subset of P. Note that in the non-private definition, inequality star implies that the convex hull of S is contained in the convex hull of P, and the convex hull of S contains 1 minus alpha scaling of convex hull of P. Why we use this bicategorical definition here that requires the convex hull of kernel sandwiched between 1 minus alpha scaling of the kappa Tukey region and 1 plus alpha scaling of the shallower kappa minus delta Tukey region, instead of using the above inequality star directly? As shown in this figure, kappa Tukey region is an equilateral triangle of edge length 2r, and S is above satisfies the inequality star. However, the minimum bounding ball of S is smaller than the minimum bounding ball of kappa Tukey region, which indicates that S is not a reasonable kernel of kappa Tukey region. Hence, for the bicategorical kernel notion, the star inequality is not enough. Agarwal et al. Proposed several simple and efficient non-private algorithms computing kernel of fat datasets. So, what is a fat dataset? A dataset is fat if its width is proportional to its diameter. As shown in the left figure, the dataset composed of those blue data points is not fat, since its width is too small compared to its diameter. And for dataset which is not fat, we can make it into a fat one by computing its minimum bounding box B, then map B into the unit hypercube, use an affine transformation T. Then the mapped dataset TP is fat. It can be shown that after computing the kernel of TP, we can get the kernel of P by T inverse. Here's an example of non-private algorithm to compute kernel for fat dataset. They discretize the space into grids which are small enough. For each grid, if there is a data point lying inside that grid, randomly add one of the data points in that grid into the kernel set. And this algorithm is easy to be made into a private one and is able to approximate bicategorical kernel privately. We expand it to private version by adding the center of a grid into kernel if in this grid there's a point of noisy Tukey depth exceeding the noisy threshold. There are some detailed proofs of the algorithm. Please look into our paper for more details. Note that the private algorithm we got is still only for fat Tukey regions. So, to make Tukey region into fat privately, What we give is some box that contains kappa Tukey region, and its volume is bounded by 5 to the power of d times d factorial times the volume of a shallower Tukey region. Then, we map that box into the unit hypercube. Note that, in this way, we can only make the kappa Tukey region into a fat one if the volumes of the two regions are close. But if they are not, we have no guarantee. The figure on the right is an example, where kappa minus delta Tukey region has a much larger volume than kappa Tukey region. B is the approximation of bicarrier bounding box of kappa Tukey region. This makes it so that mapping B into unit hypercube doesn't change the width of kappa Tukey region significantly. So, we cannot make a Tukey region into fat if the volumes of kappa Tukey region and kappa minus delta Tukey region differ so much. So, what we can do is either to verify with privacy certain conditions that assert that the two Tukey regions are close. And if so, we say that kappa is a nice kappa, and we run the algorithms and produce a kernel privately for kappa Tukey region. Or, we propose to the user a certain value of kappa privately. So, how to find such a nice kappa that the volume of kappa Tukey region and the shallower Tukey region are proportional? First, we need to prove that there exists such a good kappa. And there are existing results showing that the lower bound of volume of any non-empty Tukey region is bounded. So, there exists such a good kappa. And we are able to propose an algorithm that privately releases a good kappa. To privately release a good kappa, for each kappa up to m, we set the score of kappa to be the maximum depths how back and forth we can go, so that their volume are still proportional. It can be shown that the sensitivity of the score is 1. Hence, we can privately select a kappa 1 with high score. Then, we release kappa 1 plus a Laplacian noise. For more details and proofs of this algorithm, please check our paper. That's the end of my presentation. If you have more questions or you are interested in our work, you are more than welcome to email to us. Thank you very much.